All right, guys, are there any questions on any of the assignments so far? Any questions on any of the assignments so far? For those of you who weren't here yesterday, if you can get any of those assignments from the last chapter turned in, if you haven't got them turned in, because otherwise they'll be zeros, because I've been going in and putting those in today. Now, what we're talking about today and wrapping up 5.2 with is addition, subtraction. Addition, subtraction of these like roots is part of it, and we'll be dealing a little bit more with kind of simplifying, like we were doing yesterday and the day before. Now, with addition, subtraction, whenever we add or subtract roots, they have to be the same. The root and what's inside have to be the exact same for us to be able to add and subtract. So when we look at this first one here, where we have the fourth root of 10 plus 7 times the fourth root of 10, well, the fourth root of 10 is the same in both, yes? So realistically, what we can say and do is that, well, I have one of them, and I add 7 to it, so I have a total of 8 fourth roots of 10. And that's it. And another way that we can actually think about this or work this through is that, well, when I look at both of these here, they do have a greatest common factor of 4 roots of 10, because they are in common in both. And what we could do is actually factor it out and say 4 roots of 10 parentheses. On the first one, it factors out completely, so I'm left with 1 plus 7. Well, 1 plus 7 is 8. 8 times the fourth root of 10 is going to be 8 times fourth root of 10. Because realistically, that's what we're doing. And with a lot of these radicals and roots, we can almost treat it like a variable, because it will behave similarly to when we add or subtract like terms. And that's all we're doing, because if those roots are the same and what's inside them is the exact same, then we can add and subtract the numbers in front of them. So for number B, or letter B, we have 2 times 8 to the 1/5 plus 10 times 8 to the 1/5. Well, they both have 8 to the 1/5, which realistically, 8 to the 1/5 is just saying that I have the fifth root of 8 and the fifth root of 8. They both have the fifth root of 8. It's just rewritten in our rational expression or exponent, written as a rational exponent instead of a radical. So what would this actually simplify to? 12 times 8 to the, because I have 2 of them and I add 10 to it, so I have a total of 12. That's it. Because we can't really simplify this any further, because 8 can be rewritten as 2 cubed, which is really just saying that instead of having 8 to the 1/5, we could really say that this is 2 to the 3/5. But 3/5 doesn't simplify. It's not any simpler than 8 to the 1/5. Now, if it had been, say, the 6th root instead of the 5th root, then we would want to do this, because 3 over 6 does simplify, it does reduce. Because if we can make the roots simpler, then we want to do that. If it doesn't actually impact anything, because 2 to the 3/5, it doesn't change it. It's still the same as 8 to the 1/5. We didn't really reduce anything, we really didn't change anything. Does that kind of make sense? So that's why that's why we'll leave it as 8 to the 1/5 instead of trying to rewrite it. Now that brings us to example C. Now both of these do have cubed roots, but one of them is a 2 and the other is a 54. So the only way we'd be able to add or subtract is if the roots are the same and what's inside of them is the exact same. So before we can say that's it, we need to see, can I actually reduce 54? Can I reduce the cubed root of 54? Yes, because 2 is a factor of 54 if we did the factor tree. Because we could say that would be 2 times 27. Well, 27 isn't divisible by 2 anymore, but it is divisible by 3 and 9 is, well, we have 3 threes, and we have a 2. So for the fifth root, or the third root of 54, we can really rewrite it as the third root of 3 cubed times 2. And then we have minus the cubed root of 2. Now the cubed root of 3 cubed will actually simplify to just be 3. We can actually move it out. We can move one of them out. And what that leaves us inside is the cubed root of 2 minus the cubed root of 2. So for this one here, we really had to simplify the cubed root of 54 and actually make it in simplest form, which is 3 cubed root of 2, which actually does give us a cubed root of 2 in both, so we can subtract and get, because really I have 3 and I take 1 away, so we're left with 2 cubed roots of 2. 2 cubed roots of 2. And that's all we have to do for this here. Any questions on this? All right, let's look at some more. The yellow ones can simplify some of these, but they have issues with really indexes of 3 or higher. So the ones that we were looking at the other day that did simplify well are the 1 over, say, the cubed root of 3 minus 2. It would simplify this here. And would do that simplification, really turning it into square root of 3 minus 2. 9 minus 4 should be over 5. And it would work this out. Well, no, actually, it would just be the square root of 3 minus 2. It'll be after break. Negative plus. Because it will do those for us. Now these here, it won't do it quite so well because fifth roots, it's going to end up trying to actually approximate the decimal. So when we look at these here, so the first one, 7 times the fifth root of 12 minus the fifth root of 12. Because I have 7 and I'm taking 1 away. So this would be 6. And it would be? Times 9 to the 2/3. And really, we would leave this one here. I mean, we could technically rewrite it. Because 9 is 3 squared. So it'd be 3 squared to the 2/3. And powers of powers multiply, so it would be saying 12 times 3 to the 4/3. Right, because 12 times 3 times 3 to the 1/3, because 3/3 would move 1 out, which would just be 36 times 3 to the 1/3 if we wanted to take it all the way down. most likely the book is going to stop here. At a college algebra level, they might make you take it all the way down to there. And that's really just manipulating and noticing, okay, 9 is a perfect square. 2/3 with that extra 2 would actually get us to a whole number, so we'd have to bring it out. All right. Any other questions on these two here before we look at the last one? So, number 12. We have the cubed root of 5 plus the cubed root of 40. So we need to see if we can rewrite the cubed root of 40. So if we look at 40, well, one of the numbers that we do know that will go into 40 is 10 and 4. Well, 4 is, and 10 is. And we do have 3 2's because we're taking the cubed root, so we do need groups of 3. So that will be helpful. So what we can say is we have the cubed root of 5 plus the cubed root of 2 cubed times 5. Well, the cubed root of 2 cubed is just 2. And this gives us a total of 3 cubed root of 5. And on some of these here, if we know that, well, can we simplify the cubed root of 5 any further? No. So if we have any hope of these actually being able to add or subtract, this number here should have a perfect cube and 5. So if we divided 40 by 5 and then took the cubed root of whatever that number is, it should come out to be a whole number. And if problems like this, I mean, come up on the ACT where we actually do have a multiple choice bank, you could try typing that whole thing in and then comparing it to the decimal versions of each answer to see which one matches up. Any questions on this here? And with a problem like this here, if they didn't turn it into a decimal, we know that we'll have to have a cubed root of 5 because that doesn't simplify any further without turning it into a decimal. So any answer that did not have a cubed root of 5 would not be the correct answer. Okay. Properties of rational exponents and radicals. Okay. Most of everything we've been working with so far has been working out pretty nicely. Now, we know that if I take a number, a negative number to an even power, it becomes positive. A negative number to an odd power just stays negative. And we've worked with this before in dealing with the properties of signs, because if we said, say, -1 squared is going to be 1. -1 times -1 is 1. Now, if we said -1 cubed, well, that is -1. And we've kind of go on over these properties of a number to an even power is going to become positive, even if the number started out positive or negative. If the power is odd, well, if it starts out negative, it will be negative. If it starts out positive, it'll end up being positive. This is just some of the properties we've gone over. Now, if I took the square root of x squared, will that be the same as the square root of x squared? For some cases, yes, because if x is positive, that'll work out, and if it's negative, it will eventually take care of itself. But we do need to be careful of what the variable is, because the nth root of x to the n, because they do simplify out, if it's negative, as we see here, well, it's going to end up being negative. If it's negative and it's even, it comes out positive. Because if I took the square root of -1 squared, well, we'd end up with -1, yes? Well, come on. There we go. Now, if we took the square root of x squared, we get x, yes? But could x be positive or negative? Well, it could be either one, yes? Because we just are plugging in values. So what they're saying with this here is that whenever we have an even root and an even power with variables, we technically have to put an absolute value. Wrong way. And that's really what this is saying. When n is even, the nth root of x to the n is equal to the absolute value of x, because we're talking about the positive case. Because if we worked it out, the fourth root of 3 to the fourth is going to be 3. The negative case, we work from the inside out, because the -3 to the fourth would come out to be a positive 81. We take the fourth root of it, we get to 3. Because we have to work from the inside out. We're not just canceling, because it's not going to end up being -3. It's going to end up being positive 3. So really all that's telling us is anytime we have an even root, we're technically supposed to put the absolute value bars around it, even if we're taking the nth root of x to the n. If that root is even, we need those absolute value bars. So if we look at this here, the first one, the third root of 64y to the 6th, well, an odd root, so we don't need the absolute value bars. Well, the third root of 64 is 4. Now we need to take the third root of y to the 6th, which would be, well, if we rewrote it as a fractional exponent, because the nth root of a to the x is equal to a to the x over n. Or we can just say 2. And with the variables, it's sometimes hard to see that. We can actually just rewrite it as fractional exponents. If we wanted to, we could have actually, instead of saying 4, we could have said 64 to the 1/3. And the calculator would have done the 64 to the 1/3 as long as it works out evenly. Now, any other questions on A before we look at B? Now with B, there's different things we can do with it. And some of them is kind of combining a few steps together. What we can really think of this as is the fourth root of y to the fourth over the fourth root of, or x to the fourth over the fourth root of y to the 8th. Fourth root of x to the fourth over the fourth root of y to the 8th. Well, as the fractional exponents, the numerator would be x to the 4 over 4. The denominator would be y to the 8 over 4. Well, exactly, I mean, 4 to the 4th, 4/4 is just 1. So we could have just written x. Y to the 8th fourth is just saying that we have y squared. And since we took an even root, those variables that came out of the radical need to be in absolute value bars. Because what comes out has to be positive, but the variable itself could be positive or negative. So any of these that come out, any of the variables that come out completely will technically need an absolute value bar. If for some reason we still had some left over, like it was x times the fourth root of x, we don't need the absolute value bars for the fourth root of x. Yeah. And now the reason we wouldn't need the absolute value bars for an even root that's left over is because the root takes care of it itself. Because we know we can't have a negative inside of an even root and have real roots. So since it's still left over, it's kind of telling us this can't be negative. But when they come out fully, we need to adjust for that sign. Questions on this here? Now, especially on the test, I'm not going to be a big of a nitpick about you didn't put the absolute value bars here or you didn't need to. Because in some cases, like this one here, this is overkill. This is actually all you need. Because the denominator is y squared, yes? Any number that comes out of y squared will always be what? Positive. Because of the square, the y squared, even if y was negative, because of the square, it's going to turn it into a positive number. Since the x is to the first to an odd power, it wouldn't. So we technically only need it with x, we don't need it with the y squared. But that's, I feel, is getting a little too nitpick more, because here we're really wanting to see, can you simplify these? Can you work with this? Because that would technically be the correct answer, because we would need the absolute value of x over y squared. Any other questions on this here? So we have the next one, the cubed root of 27d to the 12th. So we need to see what the cubed root of 27 is and the cubed root of d to the 12th. Over 3. Yes. And since it's an odd root, we don't have to worry about absolute values. Any questions on this here? Had a feeling. Now on the last one, I said we could skip a few steps here and there depending on how it works. Well, as we just saw, really, we could break this up into the fourth root on top and the fourth root on bottom, yes? If we wanted to, I could actually go straight to those fractional exponents. Because I know that the denominator for the x and the y of this fractional exponent is going to be what? The 4, because we're applying it to both. And it would just be x. And the denominator, y. And we really only need the absolute value bars around the x, because we're taking an even root. So we didn't necessarily have to go from here to the fourth root of x to the fourth over fourth root of y to the 16th, and then come here and continue on. Because if we see how that works, we don't necessarily have to put that in. Questions on this here? Write each expression in simplest form. Assume all variables are positive. So with that assumption, we don't need absolute value bars, because we're assuming that they're all going to be positive, so we don't have to worry about a negative case. All right, so we have the fifth root of 4, a to the 8th, b to the 14th, and c to the 5th. Oh. So we could rewrite this as fractional exponent. So we can say 4 to the 1/5. Well, since it doesn't have an exponent attached to the 4, it's going to be 1. Now, we could have rewritten this as 2 squared, but for it to be able to reduce, I would need the numerator and denominator to have something in common, or it to be greater than 5, which it won't. Now, A would be to the 8/5. B is to the 14/5, and C is to the So when we finish this here, we're going to have numbers inside and outside of the radical. Now, I rewrite it in this fractional form because it's a little bit easier to see what simplifies and what doesn't. Now, 4 to the 1/5, as we just said, this here realistically is the same as saying 2 squared to the 1/5, which is 2 to the 2/5. Well, that's not going to simplify, that's not going to reduce. So what that tells us is that for the 4, if we're trying to simplify this expression, the 4 is just going to stay inside the radical because we can't take the 5th root of 4. Now, if we look at A, we have A to the 8/5. Is 8 bigger than 5? So that means we can simplify it. Because 8/5 as a mixed number would be what? And 1 3/5. So if we're thinking about what comes in, what goes out, well, I can take 1A out, because that would be our whole number 1. But we're left over with what? So inside we would have A to the what? It's 3/5, yes? Because the numerator, because our A, nth root of A to the x, yes? Is A to the x over n, where n is our root, yes? Well, for this here, we do have the root taken care of with the 5, yes? 3. Because A, I'll write it out, because here, what we're saying is we have A to the 8/5, which is 1 times 1 3/5, not times, 1 3/5, yes? Or, I think a better way to say this, is that 1 would be our 5/5 plus 3/5. That's the same as 8/5, yes? According to our properties with exponents, realistically, if we're adding 2 exponents, we're really just multiplying the bases. We're just going backwards. Well, A to the 5/5 is just A. A to the 3/5 is saying that we have the 5th root of A cubed. Questions on this here? So our 8/5 or 1 3/5 is really saying that I do have one whole A that does come out, and we have 3 left over inside. We're ready to look at B. Because B is to the 14/5. Yeah, 14/5 is 2 and 4/5. So that means we have 2 wholes that we can take out. We can reduce out, because we can have B squared on the outside and B to the 4th on the inside. Because that's doing the exact same thing here as what we just did, is that we're saying that we have 10/5 plus 4/5, which would be R2 plus 4/5, or simplifying it back down. 5/5 is just 1, so we have that's actually it. Questions on this here? Well, let's look at another one. Okay. All right. We'll do another one of those here in a second. Actually, before we do these other two, let's go on and do this one so that we have those two connected. I need to rearrange those problems so I have them next to each other instead of two problems away. Now, we can rewrite this as fractional exponents. Yes. Yes. Yeah. Yeah, for some reason it's disappearing. Yeah, it just depends on how they're opened up. I don't get it. But some of the times when I do have that up and I pause it and don't realize it, I'll forget. So, any questions on rewriting this with fractional exponents? Okay. Now, we can start from left to right with the 2 to the 1/3. 2 is prime. So really, 2 to the 1/3 really won't simplify. There's no way for us to get the 2 out. So the 2 will actually stay there. Now, the next one to look at is a to the 13/3. Is the numerator of that fractional exponent bigger than its denominator? Yes, so that means we're going to be pulling a's out because we can take some of the cubed roots out. As we can say a to the 4th on the outside. Because 4 times 3 is 12. Because we can say 12 plus 1 over 3 is really 12/3 plus 1/3, which is 4 plus 1/3. And our 1/3 is really just telling us that I have a to the 1st inside the cubed root. And I think the one that y'all like out of all these up here besides 2 is this next one, b to the 3/3, which is just b on the outside. And the last one, c to the 8/3. Because we can look at it the way we did for a, or for every group of 3, I'm going to take 1 c out. So I could say 8 minus 3, which is 5. So that means I am going to take 1 c out for sure. I can do it again, which gives me 2. So I was able to take 3 out twice, because each group of 3 will simplify once. And I can do it twice, and 2 left over. Or yes. Or 8 is the same as 3 plus 3 plus 2, yes? 3 plus 3 plus 2 is 8. And we know that this is all over our root of 3. So really what we're saying is that I have 3/3 plus 3/3 plus 2/3. Well, 3/3 is 1. So our 1 and 1 is 2. So I have 2 whole a's that will come out, or 2 whole c's that will come out, which would be our c squared. Because here we didn't include any of the c for this, because realistically what we're saying is we have c to the, well, 6 plus 2 over 3, because we're rewriting that 8, which would be the same as saying c to the 6/3 times c to the 2/3. Well, c to the 6/3 is just c squared times c to the So the even ones, whatever we can divide evenly comes out, and whatever the remainder is what's left inside. Because if we divided 8 by 3, how many times will 3 go into 8? 2 times 3 is 2. Well, I don't have anything left over, so our remainder is, so it's what's left inside. Yeah. Because we could have done that with any of those, because 13 divided by 3, it will go into it 4 times and have 1 left over. Questions on this here? So let's go back to this one here. Write each expression in simplest form. Assume all variables are positive. So x is already simplified. The denominator, we have the cubed root of y to the 8th. Yes? We cannot have a radical in the denominator. So, well, another way we can think of this is in its fractional form, which will tell us that we have 8 over 3. Yes? We need this to simplify out completely. We don't need to have a radical in the denominator. We can't have that fractional exponent in the denominator. Now looking at this here, 8 divided by 3 won't divide evenly, yes? What is the next number after 8 that divides by 3 evenly? 9. So how many more do I need? 1. Now, we won't just multiply by y, because we need to get the 8 to become a 9, yes? And when we multiply like bases, we add the exponents. So we're not just adding 1, we need to add 1 to the 8. So what I'm adding is actually 1/3. Because we actually need to multiply by the 1/3, because 8/3 plus 1/3 would actually be 9/3. So the numerator is going to be x times y to the 1/3. The denominator, since the y's are the same, we're adding the exponents. Yes. Because we would get y to the 9/3, which gives us y cubed in the denominator. For the most part, we could leave it as x times y to the 1/3, or in radical form, it would be x times the cubed root of y, because those are going to be the same thing. And that there's really our final answer. Yes, I would take that. We can say x y to the 1/3 over y cubed. Just be careful that you're not tempted to want to simplify the y's, because y cubed and y to the 1/3 are not the same thing. Because y to the 1/3 is really saying we have the cubed root of y. It's trapped inside there. We can't just simplify. Any other questions on this here? Okay, well, I know we're jumping back and forth. Let's look at this one here. We'll see. If we need to, we can. Now this one here, we do need to simplify that radical, yes? Well, we can rewrite it as a fractional exponent, because that does work. And why don't we go on and do that? Because we're saying that we have x squared over y to the 13 over 3. Now we're going to need to multiply top and bottom by y to the something thirds, 2/3, because the next number after 13 that divides by 3 evenly is 15. So I actually need 2 more. So in the denominator we have y to the 15 thirds. In the numerator we have x squared times y to the 2 thirds, which would give us x squared y to the 2 thirds over y to the 5th. And that would be it. For this one here, any more that we go over y to the 2 thirds, it's just adding extra ones in. Because realistically, when we do this multiplication here, the exponent shouldn't be greater than 1. Because if it is greater than 1, we're really adding a whole extra y in. We're trying to just get it to the next one that works, which should be less than 1. Any questions on this one here? This is the last one. And we need it in simplest form. We'll finish this one up here, and then we'll do the one last one tomorrow to finish this up. And this one here is actually easier than it looks, because the first thing I would do is divide the two numbers. 14 divided by 2 is 7. Whenever we have like bases, I'll answer in a second, we subtract the exponents. So it'd be x to the 1 minus 3/4. And, well, we'll finish this tomorrow so that y'all can go on to your next class.